in the first free response question that was on your practice test, you had a man that was sitting on a ledge, and then he swings down from a rope, and he grabs onto a sandbag, and then he goes flying off of a cliff, and he lands in a lake. And so this problem is a very good free response problem because it requires you to use a little bit of everything from throughout the year, other than rotational motion. This is a problem where you use conservation of energy, and then you have to look at circular motion and the idea of the net force being towards the center of the circle, the idea of centripetal force to figure out what the tension in the rope is at the bottom of the circle. And then when he grabs onto the sandbag, you have to use conservation of momentum. And then he goes flying off the cliff and lands in the lake, and you have to go through and use projectile motion or kinematics. The other thing that makes this problem a little bit difficult for some people is the fact that everything needs to be in terms of variables. It says right here to answer everything in terms of M1, M2, L, and G. So again, some people have some trouble with that, but that's a very common thing. In fact, it actually makes the problems a little bit easier because you don't have to keep plugging numbers into your calculator. You can just work through the algebra. And so for this problem, each one of the pieces by themselves is fairly simple. But the thing that makes it extremely challenging for some people is the fact that you have to sort out whether you use momentum or energy, or whether you can use kinematics, or what the key idea is. You have to figure out, is the net force 0 at the bottom of the circle or not? There's a lot of different things that really have caused people a lot of difficulties. So in this problem, to solve this, part A, it asks for the speed of the person just before the collision with the object. And so he's starting at point A, and he's swinging down to position B. So it's asking for his speed at B right before he hits the object. And for this problem, some people have trouble figuring out how you can find that speed. And there's a few different ways of finding the speed. Sometimes we have an object on a ramp, and when the object is on a ramp, it has a constant acceleration. You can calculate the acceleration, and then you can use kinematics to find what the speed is. For this problem, he doesn't move along a straight line. His acceleration is not constant. If the acceleration is not constant, then the kinematics equations that are written on the board do not work. Those only work for constant accelerations. So you have to understand when you can use those and when you can't. And for this one, because the acceleration is not constant, this is a situation where conservation of energy becomes an important idea. That was the other main method that we had of finding the speed of objects that were moving around. We use this for roller coasters. We use this for a lot of different things. Those were helpful in situations where the acceleration was not constant. So to use conservation of energy, we need to pick a height to be 0. And so since we're trying to find the speed right before he hits object M2, it makes sense to make that where the height is 0. And that means that his height at the beginning is equal to the length of the rope. So the initial height is L. If the angle was not 90 degrees like is given, you would have to figure out what that height was. You would go through and use trigonometry to figure out what his height is in terms of L. So for this problem, conservation of energy says that the potential energy at A plus the kinetic energy at A equals the potential energy at B plus the kinetic energy at B. The potential energy at point A was the mass of the man, M1, times G, times the height, L. And there's no kinetic energy at point A. At point B, that's where I said that the height was 0, so the potential energy is 0. And the kinetic energy at point B is 1/2 times the mass of the man, m1, times the velocity squared, the speed that we're looking for. And so if you solve that for v, the m1's divide out, and we get that the speed is the square root of 2gl. Being able to use conservation of energy to find the speed of an object is an extremely common idea on the AP test. It's extremely important that you understand how to use conservation of energy for a lot of different situations. For part B, the tension in the rope just before the collision with the object. The most common mistake in this is to say that the tension in the rope equals the weight. The problem with that is if I have the man, I'm just going to draw the man as a block. The man has a weight m1g. Because he's moving in a circle, the tension has to be greater than his weight. There needs to be a net force towards the center of the circle. Again, unless he's moving in a straight line at a constant speed, the net force is not zero. And if the net force is not zero, you have to figure out which force is bigger. Again, when you have something that's moving in a circle, then there needs to be a net force towards the center of the circle. So the net force towards the center of the circle is going to be the tension minus the weight. Again, towards the center of the circle we make positive, away from the center of the circle, which is the weight, that has to be negative. And the net force is the mass times the acceleration. But for something moving in a circle, his acceleration is the speed squared divided by the radius. So this is m1 times the speed squared, and the radius here is the length of the rope L. Setting those two things equal to each other, we have T minus m1g equals m1 times the speed squared. Well, the speed that he has at the bottom is that speed that we calculated in part A. So it's going to be the square root of 2gl squared divided by the radius L. So this gives T minus m1g equals 2 m1 g L over L. And the L's divide out, so we have T minus m1g equals 2 m1g. We add m1g to both sides, and we get the tension equals 3 times m1g. The tension is 3 times the weight of the person. Part C, find the speed of the person and the object just after the collision. So in this, the man grabs onto the object. And so the key word here is collision. Again, immediately when you see that there's a collision, the absolute first thing that should pop into your mind is conservation of momentum. So in any collision, the momentum is conserved. So we have that the initial momentum has to equal the final momentum. Initially, we have the man with a mass m1 moving with a speed v. Again, that's our answer to part A. And then afterwards, the man and the object, m1 plus m2, they stick together so we can treat them as one object. Again, sometimes they bounce off each other and you have to treat them as two separate objects. For this one, they do move together with some speed v final. And so the initial momentum is going to be m1 times our speed that we had in part A, the square root of 2gl. And our final momentum is m1 plus m2 times the final speed. And so rearranging that, solving for V final, we get that V final is m1 times the square root of 2GL divided by the quantity m1 plus m2. Part D asks for the ratio of the kinetic energy of the person-object system before the collision to the kinetic energy after the collision. Because this collision is inelastic, when objects stick together, that's called a completely inelastic collision. For inelastic collisions, the kinetic energy decreases. So the important thing here is we should get that the kinetic energy changes. This is not a situation where the kinetic energy before the collision equals the kinetic energy after the collision. There are forces that are doing work on the objects, causing their kinetic energies to change. But setting up a ratio either means to set this up as the kinetic energy before the collision to the kinetic energy after the collision, or it means to do the kinetic energy before the collision over the kinetic energy after the collision. Either of those are correct ways of setting up ratios. It is not correct to say that the kinetic energy before the collision equals the kinetic energy after the collision and to set everything up that way. That's not the proper way to express a ratio. Either you use a colon for the two things, or you do one divided by the other, or you'll say that it's the kinetic energy before to the kinetic energy after. So you need to find the kinetic energy before and the kinetic energy after. I'm going to use the fraction way. That's the easier way, I think, of setting this up because it allows you to simplify things if you choose. But the kinetic energy before the collision over the kinetic energy after the collision is the kinetic energy before is 1/2 times the mass of the man, m1, times his speed right before the collision, square root of 2GL squared. So again, this is 1/2 mv squared. And then this is divided by 1/2. After the collision, the two objects stuck together. Again, we have that up in the other drawing. So the mass that we need to use after the collision is m1 plus m2. And the speed that we need to use after the collision is our answer to part C. So that's going to be m1 times the square root of 2GL over m1 plus m2. And I need to take that whole quantity and square it. Now, leaving this answer in this form would be perfectly acceptable for full credit. You do not need to go through and simplify things, although if you needed this answer for another part, it would make sense to simplify it. But it would be perfectly okay, and in fact, I would suggest that you would just leave this answer this way. But if we were going to simplify it, the 1/2 divide out. When I square the square root of 2GL, I get the square root of 2GL in the numerator, or I could just get 2GL in the numerator and the denominator. So those divide out. And an important thing is, in parentheses here, I have this whole thing squared. So that's m1 squared divided by m1 plus m2 squared. So this is m1 divided by m1 plus m2 times the quantity m1 squared over m1 plus m2 squared. And doing a little more simplifying, this m1 cancels out one of these m1s. This m1 plus m2 cancels out one of these m1 plus m2s. So we have 1 over this fraction, which we invert and multiply, and I get that I have m1 plus m2 over m1. Again, if my kinetic energy before the collision is bigger, which it has to be because it lost energy, then I need to get something that's bigger than 1. And m1 plus m2 divided by m1 is something that's bigger than 1. This last part. Find the total horizontal displacement x of the person from position A until the person and the object land in the water at point D. So if I go back to my drawing, one of the things you have to be careful on is it's asking for this entire distance here. It's not just how far he travels after he leaves the cliff. We're going to find that distance. Again, we will look at this piece right here, but we also need to add in this piece right here. And if we look, that distance is the length of the rope L. So we're going to take the length of the rope L and we're going to add to it the projectile motion piece. So I need to use projectile motion to figure out how far he travels while he's in the air. So my initial height equals L, my final height equals 0, my initial vertical velocity is 0, my vertical acceleration is negative g. And so using the position time equation, I have y equals the initial height plus the initial vertical velocity times time plus 1/2 times the vertical acceleration times the time squared. So I have 0 equals L plus 0 plus 1/2 times negative g times t squared. And this gives me a time that's equal to the square root of 2L over g. Again, everything is inside that square root. So to solve this problem, we're going through and we're finding the time that it takes for him to reach the water from the vertical motion, and then we're using the horizontal motion. Again, it's a very common type of problem to have to do in projectile motion, so you definitely need to know how to do projectile motion problems. You need to know how to calculate the time that something is in the air. You need to be able to look at all those different things. This one's easy because it's not launched at an angle, but it's just as common for them to give you things that are launched diagonally. So once we have this time, we use that the horizontal distance equals the horizontal velocity times the time. And that, again, that is the position versus time equation. There's no acceleration in the horizontal direction. The force of gravity only acts vertically. And so the projectile motion piece is the velocity after the collision, which was m1 times the square root of 2gl over m1 plus m2 times the time, which we just found, the square root of 2L over g. And so our total distance x is going to equal L plus that answer that we had. Again, it would be perfectly fine to leave it the way it is without simplifying it. If I do simplify it, I have the quantity m1 plus, or m1 over m1 plus m2. And simplifying that square root, the square root of 2gl times the square root of 2L over g. Again, to combine them into one square root, bring everything in and I multiply it all together. So I have 4GL squared over G, which this gives me L plus M1 over M1 plus M2. The G's divide out, and I have the square root of 4L squared, which is just 2 times L. And that would be the final answer. Again, you do not need to simplify this, but if you do, you have to simplify it correctly. If you make a mistake, they do take off credit for that. So just looking at the scoring guidelines that they gave, for part A, it was worth 2 points. There was 1 point for any statement of the conservation of energy, writing down U1 plus K1 equals U2 plus K2, or saying solve using conservation of energy. Somehow showing that you use conservation of energy was worth 2 points, or was worth 1 point. And then going through and setting it up and solving for the correct answer, that correct answer is the second point. If all you did was you wrote down 1/2 M1 VB squared equals M1 GL, it's implied that you understood that you were using conservation of energy. It's clear that that's a kinetic energy and a potential energy, and so that would be okay to just do that. But again, it's often good to just say use conservation of energy, because if you set that up wrong, it might not be clear that you're using energy. And so if you say use conservation of energy and you set something up wrong, you could get credit. For part B, it was worth 4 points. So even though it was a very simple thing, find the tension in the rope, there were some important things. And so it was 1 point for indicating that there are 2 forces acting on the person. So if you said that the tension equaled mv squared over r, that's saying that the tension is the net force. You would not get credit for that point. If you said that the tension equaled m1g, well, that does show that you recognize that there's tension and weight. You do get credit for that point. Both of those are wrong answers, but that's how that first point went. For an indication that the acceleration of the person is centripetal, so writing down that the acceleration is v squared over r, that's what they were looking for that point. And then setting up Newton's law, so setting up that the tension minus the weight, the individual forces added together, equal the mass times the acceleration, or it is okay to just solve directly for the tension. Either of those things are correct ways. So correctly applying Newton's second law, for including both the tension and the weight, and including a non-zero acceleration. So if you said that t minus mg equaled 0, thinking that the acceleration was 0, and you said the tension equaled the weight, you don't get credit for that point. And then substituting in the velocity from part A and the length L for the radius gives you that final point. And again, it would be okay just to leave it as this final answer. You don't have to simplify it, but it does simplify down if you choose to. For part C, it was worth 3 points. 1 point for saying something about conservation of momentum. So just writing down Pi equals Pf, or saying use conservation of momentum to solve. It was 1 point for a correct application of conservation of momentum, and it was important to show that the two masses move as one object after the collision. So this statement right here, that m1 VB equals m1 plus m2 times v final, or v after, that would be enough for those first 2 points. That's clearly showing that the initial momentum equals the final momentum, and it's correctly applying the conservation of momentum idea. And so then it's going through and solving for the velocity after the collision in terms of VB, and substituting in your velocity B from the first part. and that gives you this final answer. So the third point is for correctly finding the final answer, correctly substituting in the velocity from before the collision. For part D, it was worth 2 points. There was 1 point for correctly showing the calculation for the kinetic energy before the collision. Again, even just saying 1/2 m1 vb squared, that's enough. And then for the kinetic energy after the collision, showing that the two things stick together. You needed to have both of those things in there, and it needed to be clear that you were using your answers to parts A and C. So that's what they're doing in these other parts. So this is your answer. Well, actually, this is your answer to part C. It's m1 over m1 plus m2 times the square root of 2gl. It's that quantity squared. That's your velocity after squared. This is your velocity before squared. So just the 2gl part. And then it was 1 point for correctly setting up some type of ratio. Again, setting up as a fraction, it would be okay to set it up with using a colon. But again, an equal sign is not correct for a ratio. And again, they say specifically the ratio does not need to be simplified, but if it is, the algebra needs to be correct. So if you had this expression and then you made a mistake and it did not simplify down into this, you did not get that second point. You might have gotten the first point for having the kinetic energies calculated correctly, but you do not get that final point for the answer if you had it correct, simplified things down, and goofed up. For the final part, the projectile motion piece, it was worth 4 points. It was 1 point for relating the time that it takes to fall to the distance fallen. So again, it's using the position time equation for the vertical motion. And then there's 1 point for correctly solving that equation for the time. And then there's 1 point for correctly saying that the horizontal distance is going to equal the horizontal velocity times the time. So those three pieces together, those are the parts where you're using kinematics. Those are 3 of the 4 parts. And then showing that the total distance is that distance that we had plus L. That was worth the final point. And so you could go through, and there are a few different ways of expressing the answer. And so finally, I want to just look at what the chief grader that year said about these questions. So for this question, the intent of the question was to apply conservation of momentum, conservation of energy, dynamics, and two-dimensional kinematics. So part A was conservation of energy along a circular arc. Part B was Newtonian dynamics to the bottom of a circular arc. So that's the idea of centripetal force. Part C was conservation of momentum. Part D was finding the ratio of the kinetic energies. Part E was an exercise in two-dimensional kinematics. So these were the things they had in mind. They wanted to test all of these ideas in this one question. How well did the students perform in this question? They said that it was as expected. The average score was 8.7 out of 15. So again, I've told you you're aiming for 9 or 10 points per question to be right on track. And so that would get you right around that average score. Over 30% of the students earned a 12 or higher. About 18% of the students earned a score of 3 or lower. Again, this is a fairly straightforward question. It was somewhat difficult because there were a lot of pieces to it. That's what caused that 18% to earn a score of 3 or lower on this question. But all the pieces by themselves were fairly straightforward, and so that's what caused that average score to be, pretty decent. And then they say that the common errors, they were either the result of carelessness and then the erroneous notations. So the carelessness, those were things like using the wrong height in part A, or forgetting to add the L in the final part for that total horizontal distance. Um, the conceptual errors, and these are the more important errors, the ones that definitely cost a lot more points also. The conceptual errors were things like including rotational kinetic energy in your kinetic energy equation in part A. If you're looking at 1/2 mv squared for the person, then there is no rotational kinetic energy. Otherwise, you look at it as pure rotation. You could calculate the rotational inertia. It would just be m1 times L squared. And then you would look at the angular velocity squared, and then you would have to end up going back through and solving for the linear velocity. It would be a silly way of doing it, but you could do it that way. But it would not be correct to say that there's linear and rotational kinetic energy. This is not a ball that's rolling along the ground where there is linear and translational motion. It's either pure rotation or it's something where we have this conservation of energy and linear kinetic energy. Another thing is saying that the acceleration in part B is 0. So for the people that put the tension equal to weight, that's a major conceptual error. Or going through and saying that the kinetic energy is conserved in part C instead of looking at conservation of momentum. And again, all three of those were things that were fairly common mistakes made out of the ones that I saw in the class. And those were the common mistakes that people made throughout the year. So again, go through this question. This one involves a lot of key ideas. You should be able to do a problem like this fairly straightforward. And if you can't, then I definitely would practice all of the different pieces and learn how to identify the different parts.